Hello. Today we're going to be working through review problem 3-21. This is in Particle Kinematics. Let's go ahead and get started by looking at the problem. Okay, here's the problem we'll be doing. A crate C, you can see the crate right here, it's being pulled up an incline using the motor and pulley system shown. Determine the speed of the crate if the motor is pulling the rope at a constant speed of 6 meters per second. Okay, that's what we're going to solve. Let's go ahead and put up our givens. Okay, we have a fixed support that's shown in the picture. Our main given is really that the velocity of that motor pulling it is equal to 6 meters per second, and we're supposed to find the velocity of the crate. Okay, next step, we got to draw ourselves a picture. It's a sketch, and we're going to have an incline. And draw a crate on top of that. Okay, and that crate has a rope attached to it. And that rope is going to go around a pulley, around another pulley, and finally around another pulley. But even in drawing the picture, I can put a little bit of intelligence about how I'm going to solve this problem into it. And the question I would ask you is, if we know the rope on this side of the pulley over here by the motor is going 6 meters per second, how fast is the rope going up the incline? Well, I think you can see that for every inch that it moves on the right side of the pulley, it's going to move an inch on the left side of the pulley. So the velocity is going to be the same on the right or left side of that last pulley. So I'm actually just going to make a dot. I'm going to make a dot on my rope, and I'm going to ignore the rest of the rope. And I'm going to say that this right here is my motor, and that is moving at a velocity of 6 meters per second. The rest of the problem is not needed, because whatever speed the motor's pulling it in is the same speed that it's going to be moving up this incline. Okay, there we have our picture. Another really important part of the picture is that this pulley here is fixed. That pulley can't move, and this pulley down here is attached to the crate. Okay. Okay, we can go ahead and get started. And the first step to these problems, now you can see that there's kind of two things going on here. We are talking about velocity, but we're talking about velocity with dependent motion. What is dependent motion? It means that one particle is dependent on the motion of another. What of our particles? Well, we have m as one particle and c, our crate, as another one. These two particles are dependent on each other, and we have to find out what is that dependency. To do that, remember the first step is we set up a datum. Now I'm actually going to move this m down a little so that it's on one side of my datum. I want my datum to be a fixed point. Where is a fixed point? Well, right here. This could be our fixed point, right on that pulley. Okay, and I want my m to be on this side. It could be on the other side. We just have a negative sign. I'm going to put my m here. What did I do? I just removed another fixed portion of the rope. And since it's fixed, we know the velocity of that the length between those two m's is not changing. So we know the velocity of m is over here. Okay, now I'm going to set up my variables. I'm going to have an SC that goes from my datum to C. I need my arrow. The arrow is very important, so we know what a positive and negative sign mean. So we're going to call that SC, or the position of the crate. And then we're going to have a second one that just goes to that m, from our datum to the m. We're going to call that SM. Okay, we have our SC and our SM. Now all we need to do is write an equation for the length of the rope. The length of the rope is equal to, well, let's just do it section by section. The first section of the rope that we're going to look at is right here. I'm just going to make it bigger. Between there and there, what's that length? Well, it goes from our datum to the crate, so it's got to be SC. So we're going to have 1 SC. Okay, we have another section here. Well, let's first talk about the section from here to here. Now that part that goes around the pulley, it doesn't matter where the rope is, that distance isn't going to change. So is it a length of rope? Yes, but it's a fixed length. And since it's a fixed length, once we take the derivative, that's going to go away. So there is a length of rope there, but we're leaving it out of our equation because we know it goes away when we take the derivative. The next portion of the rope is right here. Okay, and you notice that is a little bit shorter than the first one, but we could make our crate datum right here. Okay, so we're going to make our crate datum right there, and we're going to ignore this fixed portion of rope as well. So we're going to call this also SC. Notice all I did is I have ignored some fixed portions. I ignored this fixed portion, these don't change distance, so we don't really care about them because we're going to take the derivative. So we have another SC. Okay, then we have another little piece of rope here that goes from here to here. And what's that distance? Well, it's not the full SC. It's SC minus whatever this is. That portion is SM. Let's say plus SC minus SM. There's our equation for the length of the rope. Now we know that the rope length does not change. Okay, that can be a little confusing on this problem because if you remember, the initial drawing has a motor. And that motor is wheeling in the rope. So the actual length of rope that you see is changing. However, because I decided to ignore the rope from my point M, which would be somewhere down here, so I'm ignoring the rope from my point M up to the motor. That portion of rope, I'm just going to forget about it. And I know that my dot on that rope is going to be moving the same speed as it is wheeling in. So the distance from this little dot I made all the way, that length of rope doesn't change. So I know that when I take the derivative here, I'm going to end up with the derivative of that total length of the rope with respect to time, which we know is 0, because the length of rope is not changing, equals the derivative of all this added together, which would be 3SC minus SM. Okay, we take the derivative of that with respect to time, we just end up with 3VC minus VM. And that's equal to 0. So we have the equation 0 equals 3VC minus VM. Let me get rid of that picture so I have more room. And we solve for the velocity of the crate. The velocity of the crate, 3VC, is going to be equal to VM. And the velocity of the crate is therefore equal to the velocity of the motor over 3, which in this case is 6 meters per second over 3, or 2 meters per second. Okay, that concludes the problem. Please let me know if you have any questions.